In this second part of our lecture on cycles and residence time, we're going to work on developing our understanding of residence time, how it is calculated, and its significance. Residence time, denoted by Greek tau, is the average time a substance spends within a reservoir. We can estimate residence time by simply dividing the amount of a substance in a reservoir that's at steady state by either the input flux or the output flux of the substance. Residence time has units of time, as defined by, it's the amount divided by the flux, where the flux has units of amount divided by time, so it's amount divided by amount over time. The amounts cancel out and we end up with units of time. Let's use a simple tank example to explore residence time a little further. So as I said in the previous slide, residence time, tau, gives the average time a substance spends in a reservoir at steady state. So on our left here, we have a tank, which has a pipe with water flowing into it and a pipe with water flowing out. Assuming the inflow equals the outflow and we have a constant volume, we can calculate the residence time of water in that tank. So tau, residence time, equals the amount in the tank divided by the input flux or the output flux, given they're both equal in this example. And so for this tank example, tau equals the amount by the flux in. The units of tau are minutes, because over here we have the flow in given in litres per minute, and we have the stock, or the amount of water that's in the tank, is given in litres. And so the residence time units are in minutes. So given the tank volume of 1,000 litres and the flux in equals 10 litres per minute, we can calculate the residence time tau equals the amount, 1,000 litres, divided by the flux in, which is 10 litres per minute. And so the residence time is 100 minutes, or the average amount of time water spends in the tank is 100 minutes, sorry. Why is residence time useful? Residence time can be used to estimate how long a substance like water or CO2 spends in a reservoir, such as water or CO2, the time that they spend in the atmosphere. But even more importantly, residence time can also be used to estimate how a reservoir will respond to a perturbation from steady state conditions. So if we consider a tank down here that has water flowing in and water flowing out, and if they're equal, it's obviously in steady state. But what if we perturb the system? What happens if we change the input flux or the output flux? One of the key things to understanding what the changes are is that if the output flux of a substance from a reservoir is often proportional to the amount of the substance in the reservoir. This is known as first order kinetics in engineering, physics, and chemistry. So in the example that can be understood here, where we have a pipe with water flowing in to a tank and water flowing out as a result. This pipe should also occur above here. If we had double the amount of water in the tank, then we would expect the outflow to be greater by the order of about 2 times. Likewise, if we had a concentration of a substance like an element, for example, that was dissolved in the water, or salt dissolved in the water, and it had double the concentration, as in this example here, then the outflux, the flux out of salt in this instance would be twice as much as in this instance, given the water flow would be the same in this case and this case, but the concentration would be doubled. So the output fluxes of substance from a reservoir is often, not always, but often proportional to the amount of the substance in the reservoir. So taking this example a little bit further, so for where we have a tank and the input flux equals the output flux, then we have that tank and the amount of water. The tank is in steady state and the amount of water doesn't change. The amount is constant. Let's call that amount A with the subprimes SS for steady state. Now, if the flux out suddenly became greater than the flux in, then the amount of water that's in the tank would be greater than the amount supported at steady state. And we could call this excess amount of water above the steady state condition to be the amount in excess equals the amount that's actually in the tank minus the steady state amount. That excess amount of water will decay exponentially back to the steady state amount according to an equation as follows. So the amount of water in the tank as a function of time will equal the steady state amount plus the excess amount, which will evolve from T0 when there is an excess amount put in there, according to an exponential function where we have the exponent being negative time divided by the resonance time, or tau excess, where we can define tau excess, the resonance time, as being the excess amount divided by the excess flux out. So that seems like a lot of terminology, but to give you an idea how that might work, let's consider the simple example where so there's no flux in, so the steady state amount, where the flux in would equal the flux out, would be zero flux in and zero flux out. And under those conditions, there would be no water in the tank, so it would be empty. So if we make that assumption, then the way to imagine that is just that we have this tank with water in it, and then we shut off the amount of water flowing into the tank, and the tank gradually empties. So given the amount, the flux out tends to be proportional to the amount in the tank. As the amount gets lower and lower as the tank drains, the flux out will slow down, and the amount in the tank will gradually slow down further, and we'll follow a curve like this. And so that curve has an exponential form, and that would follow this equation here. So the amount in the tank as a function of time would decrease according to an exponential function like this, and we could calculate the rate of decrease by knowing the amount of excess water in the tank, this amount here, and what the flow rate out is at the beginning after we've shut off the input flux. And the amount of water would decay away like this, and it would follow this equation here, this exponential decay equation. One thing to note about this exponential decay equation is that on the basis of this equation, where the amount of time equals the residence time, the average time the water would spend in the tank normally, this value here becomes -1, and the exponent value becomes 1 over 2.718, the value of E. And so after one residence time, the amount of water left in the tank would be 37% of what there was at the beginning. So for our previous example with the tank, where the residence time, 1,000 litre tank that had a flux out of 10 litres per minute, and we calculated a residence time of 100 minutes, then after 100 minutes, 37% of the water would remain in the tank. And after another 10 minutes, it would be the amount at 10 minutes would be reduced by another 37%, hence the exponential curve. So let's take this one step further. Let's imagine if the amount of water in the atmosphere was suddenly doubled for some reason. So we suddenly increase the amount that's in the atmosphere. So you remember our diagram from the hydrological cycle here, showing the hydrological cycle where there's 13,000, that's 10 plus 3, 13,000 cubic kilometres of water in the atmosphere. What if for some reason that was suddenly doubled to 26,000 cubic kilometres of water in the atmosphere? So that's a perturbation size, or an excess amount of water of 13,000 cubic kilometres water in the atmosphere. How long would it take to return? How long would the atmosphere take to return to steady state? So, assuming the precipitation rate, or the output flux out of the atmosphere, so these fluxes here are likely to increase in proportion to the extra amount of water in the atmosphere, we can make these calculations. So the residence time for this excess amount of water in the atmosphere is the excess amount of water is 13,000 cubic kilometres per year, and we know that for that amount of water under normal conditions, then the output flux from the atmosphere would be 502,000 cubic kilometres per year. And so if we work out the residence time, we end up with 0.026 years, which equals 9.5 days. So the residence time of water for that excess amount would be 9.5 days, and we can use our equation that we had before, just looking at the excess amount and looking how fast that will decay away. So this is the excess amount in addition to the steady state amount. So as a function of time, we put these numbers into our equation. Here's the amount of excess water. Here we have minus time, and here's our tau value, or residence time value, of 9.5 days. So when we do that calculation, we get a curve like this. So we start off at 13,000 cubic kilometres of excess water, and we can see over a number of days that decreasing down to around about 0 and returning to the original amount of water that was in the atmosphere after about 50 days. And you can also see after the residence time of about 9.5 days that here we are at about 30% of the excess amount that we began with. So after one residence time, we're down to about 37% of the amount of excess water that we started with. And so if we looked at the total amount of water we had in the atmosphere, it would decay like this from 26,000 back down to our steady state amount of 13,000 cubic kilometres per year. So I hope that's reasonably clear enough to understand. And so at that point, we move on to the next part of we will move on to the next part of our learning about cycles, and that's where we'll start to use residence time and apply it to understand Earth's major carbon cycle reservoirs and the fluxes between them. And we'll be using that to predict the response to a carbon cycle perturbation, in particular looking at what the carbon cycle, or how the carbon cycle will respond to anthropogenic CO2 emissions, or the reduction in anthropogenic CO2 emissions.